So you minimize function f(x) under some constraint. First of all, you assume that x leave x lies on the unit sphere, so which means that the norm x is 1, or x squared is 1. So one common method is you can protect your algorithm. You have any algorithm, and you apply to your point x0. You choose x0 inside this constraint set, and you apply your method. So maybe this one it could go outside, and so it's not satisfy your constraint. So what you can do? The thing is you can protect it to inside the set x again. And this you can do it if your possible if your set is convex, and then you can find, if you have point outside, you can find a unique point inside that is closest to your point. Yeah, so you just simply do the projection back into your set if this method goes outside your set. Yeah. So this is a very simple way to modify any method you want. But the thing is, if you already go outside, then you protect it. So usually it will lie on the boundary, and and maybe you won't be able to go inside again. And maybe the minimum point will be inside it will be in the interior of your set, and this so in that case, this method might not work well. And actually, possible if you apply this to gradient descent, so you have so for the projected gradient descent, and people have results examples where you have function, and then you have two minimum, two minima, and then you have a line, and on that line you have a starting point for this function. And then if you consider the constraint to be inside in one half of this line, and you apply this projected gradient descent here, some points near this starting point, then the whole sequence will converge to this starting point. So it doesn't converge to minimum. So this is a very explicit example that projected gradient descent it doesn't work in general. And also, even if it works, it might not easy to compute this protection, because if the formulas to define your constraint, if it's very complicated, then it may be difficult to compute. Or if even to check a set is convex, and if this is defined by some functions, some inequality, maybe not easy to check if it's convex or not. So this this protected algorithm, it might be useful, but only if you can check that S is convex, and if you can compute the projection easily. And then another method is for the Lagrange multiplier. So if your constraint equality, maybe I can open this Wikipedia page. Oh no. I should put this. Yeah, so it's if your conditions are defined by, if your function is f, okay, you want to minimize, and it has the constraints dx equality, then the Lagrange multiplier method is to define a new function where you have new variable lambda. So the dimension lambda depends on how many constraints you have. So if you have like one constraint, then you add one more lambda. If you have like T1, T2, you add lambda 1, lambda 2. Then will be possible you have two function T1x equals 0, T2x equals 0, then your Lagrange is fx plus lambda 1 times t1x plus lambda 2 times t2x. And then the claim is that if you have a minimum for this function fx with this constraint, then this new function L x lambda, so your x will satisfy delta L over delta x equals 0 and delta L over lambda equals 0. So basically, x and lambda will be critical points for the new function. Yeah, so you reduce to finding minima with this constraints to finding critical points to solving an equation basically solving the system equation. So then in this case, if so possible the app that I mentioned before, it can solve equations, so you can maybe use it to try to find those that satisfy this Lagrange multiplier. And then there's more general method by for the Tarus-Hook condition. So it's a generalization of Lagrange multiplier method. Now you don't need the constraint to be equalities, but you also can assume them to be inequality. So now what is good about this is that if the function is simple, so you can find the point and solve this equation, and then you can do this. On the other hand, and then so you can reuse the finding roots, and I think this I explained before that finding roots of a system equation is a special case of the square root list problem in statistics classical in fitting data example. And another method is to replace your function by new function. So possible you have your constraint set x, so you have the integer and then you have the boundary and then you have the outside. So you want to change your function into something that will be formed implicit where you on the boundary. So somehow by this way, if you start from inside, then usually it won't go outside, because if you go outside, somehow it should cross this boundary and the boundary will become big. But of course, it depends on the method, because if you apply gradient descent or Newton method, they could jump outside. But for some of the methods, like the methods that use Bakakin, ISO, then usually the thing is they give this the value will not be bigger, so usually they won't jump outside. And also, but a problem with this thing is that here now you have a new function, and the minima of these functions or the critical points of these new functions may not be the same as the minima points of the function you want to solve, fx. Yeah, so then you need to be careful about how you decide this thing, and maybe there's some better ways to do this, with take care of these differences between the critical points of the new function and the critical points of the old function. And why do we care about this? So even if you just consider a problem with no constraints, so it could happen that it's better to stay as a constraint problem. Possible, maybe I think later. But one example is that if you want to find the smallest eigenvalues of a thematic matrix, so you can state it as the maybe I write. We have a thematic matrix, view matrix. And then we want to find the tan on that eigenvalue and x eigenvector. So that are is smallest eigenvalue of A. Then you can say in terms of constraint optimization, that is, you want to find minimum of this function AX. Next, what is the inner product? The constraint is X equal 1. And so this helps you to find this minimum eigenvalue. And actually, this constraint X equal 1 is a sphere with the Riemann manifold, and later we come to Riemann manifold. I will explain that this working with Riemann manifolds might be it gives you a better way. And let's see. Okay. Yeah. Yes. So now we come to another field in mathematics for the dynamical systems. And the role of dynamical system in deep learning, machine learning is to prove the convergence, help you to prove the convergence of optimization method. And here I have some pictures. Maybe hopefully you could see it. The first one, let's see. Okay, it's difficult to see, but this one, if you look at the point 0, 0, so it's an active point. You can see all the around going to it. Maybe it's difficult to see, but and this picture 001 is the repairing point, which means that all the around go out it. And this picture, this is starter point, which we mentioned before. So some of the arounds go inside and some of the arounds go outside. And then there are some other types of points here. This dynamical system, yeah, so like I said, it helps us to understand the iterative method. So if you have an iterative method and you apply it, then what happens? What can you say about the sequence n that you construct? Can you prove that it converges? Can you prove that it's a void subpoint? And now we come to the thing that I said before, that gradient descent it's it can avoid subpoint. So let's look with this simple example of this starter point. Of starter point. And also here I explain what does mean to say that a method can avoid such a point. So we have fxy equals x squared minus 1 squared, and the point 0, 0 is the such point, like we saw before. Because the gradient is 0 and the Hessian matrix has one positive eigenvalue and one negative eigenvalue. And then if you compare the gradient, it will be 2x minus 2y. And now if you apply gradient descent to point x and y, so x minus 1, y plus 1, you will go x n. delta is the called alpha, and then you break alpha equal to 0. And then the gradient is the 2xn minus 2yn. So it becomes xn minus 2 alpha xn. And then yn alpha yn.
Những ngày hôm qua thì
Which you can write
nay
like
mình
n
chụp mình chỉ quay lại cái
times 1 minus 2 alpha.
nhưng mà phần đầu nha.
And then yn times 1 plus 2 alpha. So now you start from x0, y0. Yeah, hopefully you could see if you on Zoom, you could see this. Then if you start from x0, y0, you apply this again. So it will, by induction, so you see that this one is x0 times 1 minus 2 alpha to n plus 1. Y0 1 minus alpha d. And remember that alpha is positive. So 1 plus 2 alpha is bigger than 0. So then you can ask, okay, when for this time x0, y0, and this sequence converts to 0, 0, which is the second point. And that can happen if and only if maybe not if and only if, but it happens only if y0 is 0. But if y0 not 0, then this sequence, because alpha bigger than 0, it goes repeating. So this will go repeating. It doesn't go to 0. And so you can conclude that, okay, if we apply gradient to this function, this very simple example of starter point, but it's very representative. Then the sequence only converts to 0, 0 if y0 is 0. And in this case, in terms of dynamical system, we call y0 equals 0 the stable manifold of this dynamical system at this point 0, 0. And okay, I say that we can. And about Newton method, so Newton method, like we said before, it will go to 0, whatever you start with. So now we can check with this. I say get with optimizing link, but okay, of course, we need to use to work on my computer. So let me just open and I show you what happens if you do this. Okay. So let's see if we apply those for this function. So let's see what happens. Let's do it. Yeah, so you can see it's. Okay. So now we want to do unconstrained optimization. We want to do translation. We don't need to care about this. And number of variables is 2. Number of objective functions is 1. And we don't want this. And we so for unconstrained minimization, maybe you only need to run like 100 steps or so on. For stochastic, you might need to run more. And now I just do one initial guess. First of all, I do like x equal 1 and y equal 2. So I just write a comma here. And I don't have any constraints, so I leave that. And I run this. And let's see what happens. Okay. Oh, yeah. Okay. Where the focus? Oh, yeah. This. So here I have two variables. So actually, I need to write like this: x0 square 2 and minus x1 square 2. And then I minimize. And you can see how it runs. So the first one, 0.79, this is the x, and the y is 2.4. And the next one, x is 0.63, but y 2.88. And the next one, y is 3.45. So you see that y increased like what we saw. Here we choose the negative one. Yeah, so you see that y goes to infinity, like I just claimed. I just claimed that y goes to infinity. You can see here. Y. So now possible that iteration of 83. You already see that y is almost 9 million. And so you can see that it goes away. Gradation goes away from this starting point. So we're pretty good because we don't like starting point. So let's see if we use Newton method. What happens? So I claim that it will go to so I need to use relax Newton, and I put the learning rate to 1. So you see Newton method, and let's run it again. So I claim that. So let's see what is the So in this point x equal 1, y equal 2. So let's run it. Yes. So because here, so what happens here that in theory it should go to 0, 0. But what happens here that because when we compare the gradient and the hexen here, because we do it manually, so we don't use the exact value because it's very costly to compare it. So we only use the approximation of the gradient hexen. So you don't see 0, 0 right away, but you see that they even if you compute installation maybe something wrong here. Maybe still it's still great distance. So how can I do? Maybe I need to start again. Maybe I need to start again. Now I need to use the internet. It's still the so I use nothing then. Two variables, 1 and 1, 2. Yeah, it should go to x0 minus x1. And this is very easy to use, even though if you don't know about what's about ultimate, you still can use it by listing of the this guide. Let me see. Maybe something. Maybe this is not the Newton method. Maybe something wrong with my. I need to check this. Assume it's not the. Yeah. Okay, you can see that it's not 0, but it's minus 64. It's almost 0. Yeah. Okay. So this is 0. Yes. Even if you don't compute the gradient and hexen correctly, not correctly but accurately, precisely, you only compute approximately, it still go to 0. Yeah. So you can see that is the method go to starting point. This is this is an illustration. And and we can check backtracking gradient. So hopefully it's run here, or maybe I need to close it and I run again. Maybe what happens if I do this? Yes, and then I do this. So let's see what happens to backtracking. Yeah, backtracking. Now you see backtracking is its behavior is like gradient descent in this case. Let's go to it. But interestingly enough, until now, I don't know if anyone could prove that backtracking gradient descent it can avoid such a point, even though in practice it always do this. But no proof yet. And so let me come back to this. So then, so the example we just saw is the illustration of what we mean to be able to avoid such a point. It means that outside of some very small set, in this case, the small set is y0 equals 0. If you start from some point outside this, then you will avoid such a point. So that's what it means. So, but there's some more set possible this line. If you start from a point on this, then it might go to 0. Yeah, for example, if you choose here alpha less than 1 half and then y0 to 0, then you can see that this sequence will go to 0. And then one remark is that even though in general people might say about like some point of a function like fxy x squared minus y squared or some kind of a sub point, but actually the correct terminology is unstable point of an optimization method applied to this concept. So you should be aware that there's some difference between this. For example, a starting point of this function fxy equals x squared minus y squared is actually an attractive point if you apply the Newton method, because we saw that it converts to this value. That depends on what method you apply. That you, even if you have starting point for your function, but if you apply the method, it might go to that point or it might go away there. Yeah. So you should be careful about this. And what we will do with this dynamical system is that we try to, if we have started point a function, so we want a method that for that start point, it will become kind of a repairing point, not repairing, but it's kind of kind of mostly repairing. So for most of the point, it will go away from this, like the second picture that you saw in the here. You saw here the second picture. Yes, this picture, yeah, where almost everything will go away from this, except like maybe on some small line, some lines, it may go inside it. Yeah. So this is what we want if we apply this method, some method to find it. And maybe the most useful result in that system applied to machine learning and deep learning is so-called stable center manifold theorem. And you can, if you want a good reference, then you can look at the my book for the global stability of the system, which is kind of a standard reference when you want to talk about stability of dynamical systems. And the theorem is on, I think it's on chapter 3 in this book. And this is the theorem. So let's A is Rm to R, we have C1 function, and 0 is a fixed point of H. So later we will understand what H comes from if you apply an optimization method to a function. And assume that the Jacobian are 0. Maybe okay. Maybe here I would. I missed something. So H from Rm to Rm, so it's equal in the same space, and assume that 0 fixed point between the H0 to 0. And then you compute the Jacobian, and you assume that it has at least one eigenvalue bigger than 1. So if you have eigenvalue bigger than 1, so it means that it's the unstable line. For example, in this case, what you see that we see 1 plus 2 alpha, which is bigger than 0 if alpha bigger than 0. So that's unstable. Then whenever you have an eigenvalue which is bigger than 1, then you have you can look at a small open neighborhood of this point 0, and inside this manifold, submanifold and dimension this will be strictly less than dimension of your space. So that if you start from x0 in this ball and x0 outside of the V, then if you apply this you integrate this h, then this x does convert to 0. This is And what happens is that we want this 0 is the starting point for your function, and H is your method. And you want, so if you want to apply this theorem, you need to check that your method H it is C1 near this point. Maybe not C1 everywhere, but it's C1 near this point of near the critical point of this. And then you want to check that it has one eigenvalue, the Jacobian has one eigenvalue bigger than 1. And then you can apply this and you can say that it can avoid your starting point. And a C1 manifold, C1 submanifold, which has the smaller dimension. Then in terms of measure theory, it has 0 measure. With in terms of probability, you can say that it has 0 probability, which means that with 0 probability, if you choose point in this step as the initial point, then you will avoid that point. You won't convert to that point. Let's see what it means to be avoid that point. And I will illustrate with gradient descent. This is x. And gradient descent is you apply x. If you put x in xn, so your xn must have x in fx, right? Fx. So what is a gradient? And so you want to compute the Jacobian of this map. So what is the Jacobian? So if you remember, and by the way, so this map, if you have this point, so which means that x equals x, so it means that the gradient must be 0. So this point is actually the same as the critical point of f, which is good because you want to find minimum. So you want this point to be critical point. This point of your optimization. So now your demand is 8 from này F to F.
Hai vợ chồng nó cũng là do cái tivi người ta định giờ vậy đó. Trời ơi xong dẫn con gì cả khỏi không cái sang chảo luôn. Nghe kể mà nổi cái này ghê á. Ghê ngon á. Ngon.
But if you remember, the Jacobian of gradient is the Hessian. And the Jacobian of the x because the identity. Okay. Identity minus alpha. Okay. Now if you have x, if x start, it start at point. For f.
Thì cái phòng nó rộng hơn, nó thoải hơn không bị. Cái phòng bên đây có
mình nằm nó sợ So you have a base of identity, so the identity is 1. And then because this one, if this if x starts point, so this has one negative identity. And this one is minus alpha lambda negative. So this one bigger than 1.
Hai cái bàn thờ ở dưới nhà ăn á, trong sâu á.
And then you in the situation you can apply the stable center manifold and you can prove that this gradient descent is a void starting point. So this is the proof. And actually it's simple, but it's yeah, so it's in this paper. So it's simple, but it seems that in particularly, these people they do it. And actually, I talked with one person who does optimization in France, and he said that this method, he claimed that this method, I don't know, but he said that this square method was known before to the Tom or someone. This group. Okay, so what happens is that there's some condition in this stable center micro hidden, but in this group they need to define that this extra is isolated starting point, which means that in the neighborhood of it, you see the unique critical point. But then later, these people, Banagas and Pili they show that you don't need this condition, that this one is isolated by using the result from what to say. I think this in A1 mark, A1, A1. What the name of this? I think this in the second year of undergrad mathematics. It's called the linear log lemma in calculus or method theory. There is not linear log lemma. With the thing is, you want to at its certain point, you want to get out one small open set that you can apply this. But if you have if this starting point is not no determinant, then it's very problematic because you have too many, you don't know what to get. But this lemma said that if you choose just discrete set of this, not discrete set, but a countable set of this starting point, and in terms of this, if you suppose that this theorem applies to this starting point, and then this will cover this set, the open set will cover the whole set of starting point, and then you can avoid this. And then after that, there's some additional improvements where people prove possible that there's a paper calling that for most first order methods, then you can avoid starting point. If you want to be precise, you can look at these things. But like I said before, gradient descent, it doesn't have convergence guaranteed globally. And also for all these additional improvements, which they can prove avoidance of certain points, they also need also these algorithms they don't have global convergence. So then this method pattern convergence descent, it has very good global convergence. I think we said it, but if you want to look some result, you can look on the paper with I wrote with Trương Trung Tuyến, I presented yesterday. And the interesting thing is that even though people prove that for most first order methods, you can write something, they cannot prove this for this pattern configuration. And what's the difficulty here is that because in pattern configuration, you change data, you change the learning rate alpha, so it's not constant, but it's changed. So one consequence that your function may not be C1 near the critical point, near starting point. And a condition to apply this stable center method is that it needs to have geometry to be C1. That's the one thing. And one other thing is this kind of changing of the alpha n, it's unpredictable. You don't know what alpha n you get next time. First of all, now for the step 3 you get 1/2, but step 4 it could go to 1/4, but step 5 it could go to 1/2 again. Yeah. So we don't know. So it's kind of like random. So in actually pattern configuration really like the random concept, and it makes it difficult. So if you want to prove for this, prove that mapping gradient descent can avoid certain points, maybe you need to to work some kind of random dynamical system. And actually, I met this my soup, and I asked him if he know any result about this kind of stable center manifold theorem for random dynamical system, and he said no, he doesn't know. That's interesting. But one thing to remark that I think that market integration can provide some points. So one thing is that whenever you run experiments, you see that it can provide some points. So that's one thing. And secondly, actually there is one variant of this market integration that you can prove that it can provide some points. Yeah, so there are two evidences for it. Newton methods. So can we? Of course, we know that Newton method it cannot avoid such point. But then the question is, can we improve Newton method so that it can avoid such a point? And the answer is yes. How you do it? How you do is that okay? If you look at possible this f x y x square and y square, so the representative example of such a point. Then if you compare the Hessian matrix, it will have two eigenvectors, 2 and minus 2. And the fact that it cannot avoid such points is of this minus 2 thing. So what do? You could what you could think about, like you could change the minus 2 to 2. And then you can do it. And this is in this paper that I mentioned that there was when I did was random to optimization. I will send you this example. And you see that. But from this cái
mình cũng nói
not like straight in the center. But for what I illustrate for with this method, if you want to generalize it to general function, you need to do something more. Let's see. Now, the question again. X square of y square, and then I can get a gradient. And it's 2x minus 2y. And I can get the x. Like 2 minus 2. And for this, make it A. So the Houston method, what you do is not you do x1, y1 equal x0, y0 minus a inverse gradient. And you can do if you compute this exactly, if you have precise value for this, so you can do 0. So now what happens if instead of making A, you do this making B? You see mostly the same like A, except that you change the minus 2 to 2. So you want to make all the eigenvectors to be positive. If you do this, you go into your method or your method, so you make x1, y1 equal x0 minus y0 minus b inverse. Now x0, y0, and then you can write x0, y0 minus 2 inverse. So it's be 1/2, and then multiply with this 2x0 minus 2y0. And you can check that it gives you 0, but now it's not 0 anymore, it is 2y0. And you can iterate this n times, and x n y n will be 0 to the n y 0. And you see that by this simple change of the eigenvalues from negative to positive, you won't go to 0, you won't go to such a point, except if y 0 equals 0. And this is the same phenomenon like for gradient descent. But then if you want to do this in a tensor function, and then some difficulties because first thing is what if the s is 0? It's not invertible, so you have a 0 eigenvalue, and you need to add something to make it invertible. And then also, there's something more you need to do. But this is one of the main ideas that you change the eigenvalue from negative to positive. Then Newton method will actually this Brownian Newton method will avoid such a point. And now one important topic in the system which actually people also now try to use it for deep learning is the flow method. Is that you have a close relation between iterative method and what's called the flow. So for example, if you have an iterative method like xn plus 1 equals xn plus uxn, then you can replacing xn plus 1 as xn by you can replace x n by t, and then xn like a function x in t, and xn plus 1 minus xn by dx over dt. And so you have a corresponding OBE x plus x derivative t equals uxt. So yeah, this called a flow. And so now what to say about this convergence is that you start from some x0, x up to equals 0 equals from x0, and you run you solve equation, you find a solution for this, and you want to know what happens if t goes to infinity for this xt. So it's the same like this is xn, and then you want to know what happens when n goes to infinity. Now, so now not n goes to infinity, t goes to infinity. You want to know if this will converge to a minimum for this for some function. For example, if you have gradient descent, then the gradient flow will be x from t equal minus the gradient f of the xt. And then the Newton method, then you get x from t with minus s of the xt inverse gradient f of xt. So one thing to notice is that usually flow is better, flow behaves better than the discrete version. For example, the flow version of gradient descent, we call the gradient flow. Then it's we come later that Rosa in which he device is Rosa in which condition will come later. And he proved that gradient flow converges for this if the function f has this condition. In particular, if the function f is analytic, then you have convergence. Or the Newton flow, actually you can do something, and it's very much similar than the Newton method. But now, but this has some. If you go backward, then it means that even if what happens that you have some discrete version, because this is what you can do in practice. You can do calculations, and you don't know what happens to it. So then one way is to study flow method first. Maybe you can prove that the flow method is convergent. So it gives you some average that maybe your method, your discrete method is good. But then when you go back, then it will not automatically that your discrete method also good if your flow method is good. possible like gradient descent. For the flow, you don't need to put any learning rate. Even if f is has the gradient of f is continuous, but if you go to gradient descent method, you need to put some learning rate so that you have better convergence. So something to notice that even if you prove that the flow is good, it doesn't imply that the discrete version that you started with would be good. And some people use this correspondent ODE, yes, discrete version to study deep neural networks, in particular to study the convolution neural networks. The idea is not okay. You can think about like is the if you have deep neural network, then it's like you have an input and then you get output. It's like an iterative method, and then they think about like between two layers. You could think about this. So it's like if they have the same dimension, you think about it like discrete version of a flow, and then they study the flow, and maybe they can prove for this kind of flow is better. So first of all, some people like we learn we study this type of thing. So you know that, and that's why I mentioned, because this flow usually it helps you to understand your discrete version. And also if you go back, like for example on ODE, then you see in general you cannot solve it. So you need to describe it. Possible use one method, Euler method, in to solve ODE, and it's if you think about Euler method, then it go back to this. But there are also other methods with higher order, and they may be better. But again, even with this higher order method of discretization, you don't have guarantee that you have good converters. And maybe let's see. Maybe I can try. Let me see how many weight this. I think this will be not too long. Yeah. So maybe I can finish this, and tomorrow maybe I advertise that tomorrow we will talk about a more interesting thing. It will be related to also we talk about something about like what we want to think about it. What we put some questions that we can think about, and one of them is what is the status of the large language model now, and first of all, you might read some news that Google, they have or DeepMind, they have some. I think that they can solve Olympic multiple question, and then what should we think about this? Does it mean that now large language models, they are very good at math? Like what you should maybe you should try to believe from what you read in the news, and I claim that it's not. But tomorrow we discuss. Let's finish today with this methodology, which is also one of the ways to improve convergence. And maybe it also one actually like you see most of the mathematics that we need in here you already learned from undergrad study. So but the thing is how you use this, and also you need to use some more. But I mean, to understand most of the mathematics, to understand not to prove things, but to understand things, then most of what you see in learning, machine learning, actually the math that you need is just from underground mathematics. They very useful. Maybe I don't know. I'm not sure about dynamical system. Maybe dynamical system. Probably you need to learn it in in graduate school, and also differential geometry. But the part of differential geometry would apply to machine deep learning. Machine deep learning it has application, but I mean for most of the practical purposes, you don't actually need it. But for semantic topology, that is just in undergrad, maybe second year undergrad. And you see another way to prove convergence. Actually, this one for dynamic system, the goal is to prove that you can avoid such point, and from this kind of metric topology, it helps you to prove global convergence. And you have several many ways to define metric possible. You could use the usual, you can distance, or you have one metric like the sum of absolute value instead of the power, and you could use any power p, the LP metric. And this L1 metric is useful in some problems involving matrices, even though it's not differentiable. And then this is kind of the standard metrics that you can modify. Possible if you think that the xm, the m coordinates should not should not be very important. So you put maybe the coefficient there. So it means that if you want this to be small, then xm and ym should be very close to each other. So and every regularization. So yeah, I mean, usually, for example, in this machine learning thing, so at the end you have some metric thing, or you have optimizing problem, and then in the machine learning community, they see that if you add something like LP, everything inside it might have conversion to a better thing. And from a viewpoint of theoretical viewpoint of y, and then here is one explanation is that usually if you have function, it might not be good, but if you add if you perturb it a little bit, then it will become a Morse function. So I recall what does it mean to be Morse function? Morse function is function so that any critical point is non-determinate, which means that the Hessian matrix has no zero eigenvalue, and condition is that consequence that the set of critical points is discrete. So every critical point is isolated, and Morse function is very useful and very important. And if you disturb a little bit, then and you have Morse function, and usually doing optimization for Morse function is easier. Somebody you can prove that backtracking gradient set. If you apply to Morse function, then it either converts to you can prove it converts to local minimum, or it goes to infinity. Or if you apply this method BFQN, the second order method that I mentioned before is also doing this. And an important convergence theorem is this resolved by Asik and Adamovic. So this the statement is very simple. Let X be a compact matrix space. So hopefully you know what it means to be compact matrix space. And let Xn be any sequence. And assume that you have limit of the any two consecutive points go to zero. And let S be the set of cluster points of Xn. That's the set for X star, so that subsequent converts to this. Then S is a connected set for this result. And how can you use it in proving convergence of optimizing method. Thing is that in many algorithms, under some appropriate conditions, you can prove that if you apply this method to a function, then the sequence you converse will you contract it will satisfy this condition. That limit go to 0. So now you want if you want to literally apply this method, you want this sequence, you want to know that this sequence xn is contained in a compact set, and that's the people you have some ways to assume it. First of all, you can assume that the set of the what's called the sub-level sets compacts, and if your optimization method it has the property that the value of the next point is smaller than the value of the before the point before it, then because the sub-level set is compact, so all these will be xn will be contained in a compact set, which is the set of point x star, x square, fx delta equal x0, the point that you started with, and then so you have so you just take x to be this set sub-level set, and then you have this, so you can apply this theorem because this set is compact, so then the set of plus point of x must be connected. So now if you assume that this set of plus points of this is discrete, which means that every point will be isolated. Then we know that if a set is connected and discrete, then it must be either empty or it's only one point. If it's only one point, that means that the whole sequence converges to this point. And so how can you show that this set is discrete? So the thing is possible if you can show that any cluster point is critical point. And then you assume the condition on the set of critical points of F. So you assume that critical points of F are discrete. Also, if F is not consistent, then you have this convergence. So you can prove the convergence. Yeah. So this help you to prove convergence. So another way to prove convergence is to use this velocity condition which we found later. Now, in general, this xn might not be contained in a compact set absolutely because we don't know, because maybe the function doesn't have compact sub-level set. So can you do something? And yes, the main idea is you just if you look at like RF. So it's RM. So we call that convergence is the only topological property. It not depends on the metric. It's more about topological. So actually, this RM so it's not compact, but it's constant in so-called real projective space. PM of the same dimension. And what happens that is it's not contained at the metric space because the metric here is infinity. This one is compact. It's not contained as a sub-metric space, then it's contained as a sub-topological space. And if you have sub-topological space, then you convert this and it's the same. Yeah, it's the same. And now thing is that you can apply this the previous theorem to this thing, and then you have this set S. But now you think about it's like in this BM, and it's connected, and then you can do the same. So what happens is so what happens possible? So here is the maybe I will start with this. But so what happens is n equals 1. N equals 1, then this is R. And for the P1, you can think it about like a circle. This point, like this. So R is a line, but then P1 is kind of a circle. And now you have this set X. This must be connected. Right? So it must be like something like this. If it's either it contains infinity or not. If it's not containing infinity, so it's totally containing R. So they're connected in R. Or if it's containing infinity, but it's connected, so it will be like this. So if you look at it as I said in R, so you think infinity, so it will be not connected, so it might have two parts. This and this. It's not connected. But then if you assume something like the set of critical point is the grid, and if you can prove that your sequence at any critical point will be critical point, then you can apply again the same thing again before. So you can so you don't need so you can prove this converted more generally. You don't need the assumption like compact subtables and so on. Yeah. So this and then you can state, so this is what we can state in general. And also you can do this for this, yeah, so you can apply this for bucket pin, for instance, or this method we can with the second order method. And then next I come to another way to prove converted, which is vector, because here you don't need the function like mod function, but you need something more analytic function. And the good thing about this is that this set is very big, and most of the case you see in practice, if you belong to this set, for example, most of the function you see in different records, they belong to this thing. Yeah, so so this so this picture. So tomorrow I will talk about this and thing, and then also the thing I discussed about what I think about this large language model thing, and so we this yeah, it's quite late, so let's stop today, and thank you. See you tomorrow.
Ông nó khó chịu hả? Nó đã nhắc người ta đi về người ta ý kiến. Ý kiến như vậy mà gì mà dọa. Nó thân như thầy Kiều Hùng các kiểu hả?